All right, next we have Gvozden, Nešković. Yes? Yeah? All right. Working it. He's from the Frankfurt Institute for Advanced Studies. He's a PhD student in the field of high-performance storage and data reliability at the Frankfurt Institute for Advanced Studies and GSI Institute in Darmstadt, where he works on performance improvement of large, Lustre, and ZFS deployments. Gvozden, it's all you.
Thank you very much for the introduction. Today I'm going to speak about the recent development of Vectorized RAIDZ implementation for ZFS. So a few facts and numbers about us. We are GSI is a Helmholtz Center for Heavy Ion Research that does research in heavy ions and nuclear physics. It's a research center based just outside Darmstadt, Germany. There are other fields of research like biophysics and medical research. And the fair is international collaboration that's currently being built at the grounds of GSI. And on the first image, the red part signifies the fair experiment that's being built. That's a facility for antimatter and ion research. So we also run our own high-performance computing and storage. We just recently moved into the new data center that's called Green IT Cube, and we run several compute clusters, Prometheus, Kronos, and several Lustre clients, where the latest NICs is based on Lustre 2.5 and uses ZFS for the OSS servers. And with some new upcoming experiments that are going to deliver raw data in throughput of about 1 terabyte per second, and they will require the Lustre I/O of 1 gigabyte per second when they are done with the event selection rate. The event is pictured on this here. It's a reconstruction of collision that's happening in the detector. So here's the standard slide that we already seen today, why we chose ZFS. We traditionally before used the RAID 6 controllers to do our reliability, but with ZFS we stand to gain other features like data and metadata checksums, compression. It also can do availability in runtime, scrubbing or silvering of the failed drives, and it supports software reliability. So, as I said, we based our OSTs on the RAIDZ level 2, which added additional pressure on our CPUs because we don't do hardware RAID controllers anymore. So basically, what is RAIDZ pool or VDEV? It's an error correction scheme, erasure scheme that uses specialized Reed-Solomon codes in an erasure scheme. Erasure means just that knowledge about failed or missing data is coming from somewhere else, like checksumming is flagging some disks as unreliable, or we just replace the disk and we know that it's empty and we have to reconstruct it. One important difference between hardware controllers and RAID-Z levels is that the stripe size is dynamic, and we have to know the geometry of the stripe to use the underlying error correction codes properly. So this is a bit much, I think. There's a math behind all of this. Basically, the codes are based on the vector extension of a binary Galois fields denoted as GF2 to the power 8. This is a finite field mathematics, 256 elements. So basic word size is 1 byte. And the erasure code is specified by these three basic equations for the parity. So pair parity is only built for RAID Z1, P and Q are built for RAID Z2, and all three are computed for RAID Z3, where D0 to Dn are data sectors, data that are coming from the data disk, but N is not a number of disks that we put in a pool. It actually corresponds to I/O size and the stripe geometry I was talking about previously. And these 2 and 4 coefficients are not actually 2 and 4 numbers. They are also elements of the field, but their decimal representation corresponds to 2 and 4, so for simplicity, let's just call them that. So from the equation, we see that we need to efficiently implement the addition and multiplication in this field. So luckily, this construct is using carryless operation, which means that addition is carryless, that in computer science term corresponds to XOR operation, which is good because it's efficient and can be efficiently computed in scalar and vector versions. Also, good coincidence is that subtraction is completely equivalent to addition. But multiplication, where we hit first roadblocks and problems. From these equations, we see that we need to support multiplication by 2 and 4 elements, but also we'll later see that sometimes we need multiplication with a constant element of the field, which is not easily done in the scalar version. We have to resort to the two lookup table, logarithm and exponential lookup tables, we can only do this at the byte level, which is not fast. For the parity generation, RAIDZ Z1 is a simple XOR parity, we all know. RAIDZ Z2 and 3, we can transform the previous equation to this form, and now we lose all the powers of 2 and 4. So now we see that we only need these specific operations computed efficiently to get decent speeds out of the computation. So luckily, these are very specific operations that can be done with some bit fiddling magic, and they can run efficiently on the modern superscalar CPUs. So we'll see that using vector instructions, we can do it even better, but this is usually sufficiently fast for the operation. For the reconstruction path, when using only P parity to reconstruct missing data block, it's again trivial because the subtraction equals to addition, and it's just again XOR of all available data blocks to recover the missing data. But basically, when we have other codes, when we, for example, have 2 failed disks, and we need to use P and Q parity to reconstruct, there's 2 ways to solve the equations. First, less efficient way is to use direct solving, and sometimes called matrix inversion method. This is used by original RAIDZ Z3 methods, and we'll see what kind of penalty in speed we encounter there. We also see that it requires, when we solve the parity equations for missing data, which are denoted as dx and dy, we need to run n multiplication with constant in this field, and this is not efficient. Other ways of solving the equations is using syndromes. Basically, we first compute, again, a checksum where we set the missing data parts to 0. And then we reduce the parity equations to the equation shown here in the middle. And then we can solve for the missing data blocks And in the final results, we see that we only need to do few of the constant multiplication to obtain the results. And we do use the previous generation method, which is much faster than direct solving. So how we vectorize this missing part, which is multiplication by constant. So in this Galois field construct, multiplication is defined as a modular operation, where this cross product is wrapped around the generator field polynomial, which is, again, there's no CPU instruction that will do this efficiently for us. But we can resort to other means. There are, in literature, there are other algorithms that can do both parts efficiently, but we don't even have to do this because we always multiply constant with the data elements. So we can rearrange the math to use lookup tables. And with some massaging of the lookup tables, we can fit them to use together with shuffle vector instructions, which in turn means that we can perform efficient multiplication by any constant of the field with just issuing few shuffle instructions. So the table on the right shows operation throughput, this basic operation, building blocks operation of the RAIDZ math. For addition, a scalar version can perform 8 byte additions at once. So SSH can perform 16 and AVX version can perform 32. Again, with multiplication by 2 and 4, the scalar version is somewhat good, where SSH and AVX2 can perform in constant time multiplication by full register size. But the issue with multiplication remains for the scalar version. We can only do 1 byte at a time, where with this lookup tables, we can perform full native register size for SSH and AVX2. So my contributions are full implementation of all RAIDZ operations for scalar, 32 and 64-bit, and also the SSH instruction set implementation and AVX2 instruction set implementations. So this is a benchmark in Userspace that uses the same functions from ZFS, but without the rest of the ZFS file system, just to compare the difference between the instruction sets. So this is a RAIDZ2 with 8 data disks that simulates 8 data disks, 2 parity disks for generate parity and reconstruct 2 data disks, which is the slowest operation in this RAIDZ2 regime. For the y-axis, we see per disk throughput of the operation, and on the x-axis is a data block size per disk again. So if we, for example, use the I/O size of 1 megabyte, that would correspond to 128 kilobyte per disk size. And we see that, basically we see 3 regimes of operations of this code. So the first on the left, we see the effects of L1 cache, which for example, for AVX2 implementation, which will mean that it's gonna be only limited by a memory throughput of the single core. And also this regime is not really realistic to be encountered in the real system on ZFS. We don't expect our whole data I/O to be in level 1 cache. The middle regime is a little bit more realistic. So this is effects of level 2 cache. The CPU I was using is a Xeon with, I believe, 25 megabytes of L2 cache. So it's entirely possible that checksumming will be run before RAID parity calculations, and that we'll find data actually in level 2 cache. And on the right, when we completely increase the data size per disk, we see the limitation of streaming data from memory to single-core CPU. And for SSH generate and AVX generate function, this seems to be a bottleneck here. Okay, same graph for RAIDZ 3. Just this time is, again, a data disk with 3 parity disks. Generate all 3 parities and reconstruct three failed disks. Just this time, on the y-axis is a log axis to see the difference with the reconstruction of RAIDZ 3 methods. As I mentioned, they use, in the original version, which is red line on the bottom, they use this direct method of solving the problem, which is very inefficient. Those 3 regimes are again present, but are just obscured by the log axis here. So these are profiling with flame graphs and perf on Linux. The same scenario for RAIDZ 3 was run on the RAM disks. And here is the original implementation and AVX implementation compared. The best way to see is to compare it to the Fletcher checksumming method, which is shown here on the left part, which stays the constant basically on both, but the parity generations shrink considerably. It's even cannot fit in that field anymore. So I come to the implementation speed up comparison between new implementation and the original RAIDZ implementation. So first part is used only, these are all RAIDZ methods that can be encountered. First part is only used for RAIDZ 1. First and second part functions are used for RAIDZ 3, and all functions can be used in RAIDZ 3 pools. So the new Scalar version, it performs marginally better for RAIDZ up to RAIDZ 3. And then we see with reconstruction, we gain speed because now we switch to the syndrome decoding method. Also, the SSH and AVX methods are somewhat better for up to RAIDZ Z3 because we most likely encounter the memory wall of single CPU core. But with the reconstruction, especially on RAIDZ Z3 at the lower right, we see the improvements of 50x, which is nice. So the summary, what are the benefits of the vectorized RAIDZ methods? It's faster parity generations, which means in turns that your CPU load on the server will be less. Or we should expect the faster recalculation of the missing data, resilvering of the pools, and which in turn can increase the reliability of the whole system. Also, we can think about expanding the pools to use more disks, which can decrease the acquiring and running costs of the whole systems. So the future work here is to test, verify this implementation, and try to upstream this to ZFS on Linux. The pull requests where these patches live is already on the ZFS on Linux, and it applies to the master branch and also on the scatter-getter work that's being done for ZFS. And some other future work that can be considered is to make the scrubbing linear, because currently when scrubbing is run, the ZFS goes through the metadata, and as soon as it encounters a block that needs recalculation, it issues the I/O for these blocks, and these I/Os can go all over the place over disks. So one idea would be to somehow sort them to the logical drive addresses and then issue the IOs to help speed up the scrub process. So thank you for attention, questions.
It's impressive. Really cool.
Thank you. Align. Basically,
can you repeat his question? Could you use the mic?
Sorry.
Did you align your data before calculation?
For this part of calculation with vector instructions, we only need 32-byte alignment. And this is guaranteed by some internal allocations in the ZFS internals. So there's no need. This is just drop-in replacement. You can run it without setting any new parameters or things like that.
So you may have answered my question just by saying that because you say it's drop-in. As we know, there are other instruction sets out there. There are other vectorized processors. ARM with Neon, of course, comes to mind. Do you think that the structure of the code would make it straightforward to ZFS to take advantage of these other instruction sets on other processors?
Yes, Neon definitely can do the same instructions that are required for this. But we concentrate first on x86. The patch that allows vectorized code on x86 is already in the master of ZFS, and now the other implementations of checksumming and RAIDZ calculations can go in.
It is great improvement in speed, like by factor 60. And so we limited when we choose number of data disks. We look on reconstruction time, and this puts the limit. So right now we have like 40 hours. In your configuration, you had like RAIDZ 2, 8 plus 2.
Yes.
It will be nice to see what is speed improvement for larger number of data drives, like 16 or 18. So that can give us some guidance.
As I said, the plots I showed are just Userspace runs of the code without any other ZFS functions, without any disks. It's just from memory to test, to compare the implementations between each other. As I said, the actual scrub algorithm can use some work to make these random IOs that's being issued to the more linear IO to speed up things. So you will, in the real system, you will get for sure the lower CPU load, but the guaranteed throughput improvement, it cannot be guaranteed, basically.
Actually, you just answered my question, which was if you had a feel for what actual I/O effects would be.
Yeah.
So, okay.
So the patch, there are some first testers, they report there's no data corruption. We don't have, fortunately, anything faster than hard drives, so maybe with SSDs or even something faster, someone could get a feel.
Okay. All right. Thank you very much.
You're welcome.